Welcome to this explainer. Today, we're diving into a genuinely wild, highly counterintuitive engineering dilemma that's playing out right now in our power systems. You see, we're rapidly transitioning to a beautifully clean, renewable grid, but in doing so, we've kind of accidentally broken the fundamental laws of how we keep that very grid safe. So let's jump right in and unpack what engineers are calling the green grid paradox.
Let's start with a stark reality. Picture this. A tree falls on a power line, or maybe a massive transformer suddenly fails. It creates a short circuit. Now, on our traditional grid, these faults unleash an absolute flood of violent energy. We're talking metal-bending power that requires heavy-duty protection, specialized switchgear, and honestly, sometimes brief firefighters just to manage the aftermath. It's a brute force problem. But what happens when that same grid is powered by wind? You might intuitively think, well, modern wind turbines would just add to all that electrical chaos, right? Actually, no. And this is where we hit a terrifying twist in the green energy transition. As we swap out those old power plants for modern wind turbines, the danger completely flips. The problem is no longer having way too much current during a fault. Suddenly, it's about dangerously having too little. Part 1, the explosive old grid, brute force, and massive currents. To really wrap our heads around this paradox, we first need to understand the baseline. We have to look at exactly how our traditional power grid was built to operate, because you have to know the old rules before you can understand why they're breaking. In the old grid, the real workhorses are what we call synchronous generators. Think of your classic coal, nuclear, or hydro plants. These machines act like literal brute force iron giants. Because their magnetizing flux is controlled by a physical field current, they carry incredible momentum. So the very millisecond a short circuit happens, they literally dump all of their electromagnetic power directly into the system. There's no filter, no hesitation. It's just an immediate, physical, violent reaction to the fault. So what does that actually look like on paper? Well, when a fault hits one of these traditional systems, the subtransient current, which is just the current in those first few critical milliseconds, absolutely skyrockets. It jumps to 4, sometimes even 6 times the normal operating limits. It bursts out in this violent, asymmetrical, decaying wave. And here's the kicker. Our entire global power grid safety systems were designed over the last century to look for exactly this massive 600% spike. Moving on to part 2, enter the Type 4 turbine, the digital firewall. Let's fast forward to the modern era of converter-fed generation, specifically the modern wind turbine, and see how it completely rewrites the physics of the grid. We are rapidly transitioning away from a world of heavy, spinning, iron synchronous generators and moving toward a grid heavily dominated by wind, solar, and highly advanced power electronics. This isn't just a simple change in the fuel source we use, it's a fundamental change in the electrical machinery itself. The most advanced wind turbines on the grid right now are known as Type 4 full converter turbines. Unlike those old iron giants we just talked about, a Type 4 turbine's generator is completely physically isolated from the power grid. Between the turbine itself and the grid sits a massive array of power electronics. Think of it like a highly trained traffic cop facing down a flash flood. While the old generator bursts like a broken dam, the modern Type 4 turbine uses its power electronics to act as a strict digital firewall, meticulously buffering and regulating the flow of electricity. Just look at how a Type 4 turbine behaves during a severe fault. Even when the grid outside is in a state of absolute, chaotic short-circuit emergency, the power electronics of the turbines stay completely calm. They output this perfectly balanced, symmetrical sine wave. The electronics are just so smart and so incredibly fast that they actively manage the current millisecond by millisecond. And here is the magic number. Remember how those old generators spiked to 600% during a short circuit? Well, the power electronics in a Type 4 turbine tightly clamp the fault current to just 110%, maybe 120% tops of its normal rated output. It instantly spots the fault, says, "Whoa, that's dangerous," and artificially caps its own output to protect its sensitive internal components from literally melting. Which brings us to part 3, the low current paradox, when safety becomes a threat. Now, limiting a massive explosion of energy during a fault sounds incredibly safe, right? Capping the current sounds like a brilliant way to protect our expensive equipment. But this is exactly where the core mystery of this explainer comes in. Think about it. If the current is perfectly controlled, perfectly symmetrical, and safely capped at 110%, what on earth is the problem? Why are grid engineers losing sleep over this?
Well, it's time to reveal the dark side of this perfectly controlled, low-current output.
Here is the crucial catch. Our decades-old safety relays, the actual circuit breakers of the power grid, they need that violent 600% high current brute force to trigger. They are basically listening for a massive explosion. So if a tree falls on a line powered only by wind turbines, the current only rises to 110%. To a traditional protection relay, a 10% increase just looks like someone turned on a few extra air conditioners down the street. The relays are practically blind to it. And because they don't trip, the fault is left burning silently and incredibly dangerously on the live network. Let's move to part 4, rewriting the rulebook, the engineer's dilemma. This exact paradox, the mind-bending fact that green energy actually starves a fault of the very current we rely on to detect it, is causing massive headaches for electrical engineers everywhere. They are being forced to completely rethink and essentially rewrite the classic safety rules and models of the power grid from the ground up.
To figure out how to safely configure the grid, engineers rely heavily on computational standards. But recent studies out of Brunel University show that older computational models, like the international IEC 6909 and even the newer UK standard ENA G74, are actually failing us. When you look at these models, they rely on approaches like nominal bus voltages or pre-fault load flows. But their fatal flaw? They simply treat these modern wind and solar plants as constant current sources. They just assume the turbines will pump out a flat line of current during a fault, which we know isn't true.
Now, these models were intentionally designed to be conservative, right? To find the absolute worst-case scenarios for a switchgear, but they fundamentally misunderstand the software running these modern turbines. Research shows these standards completely ignore what's called the voltage threshold failure. The power electronics, specifically grid-following inverters, don't just blindly output constant current. They actually only trigger their fault behavior if the network's retained voltage drops below a very specific pre-programmed threshold. If the voltage doesn't dip low enough, they don't react the way the models predict at all, and that leads to some highly misleading safety studies. And honestly, if that wasn't concerning enough, the Brunel University research reveals a massive, glaring hole in the current rulebooks. The absolute newest technologies hitting the grid right now, things called grid-forming inverters, which artificially simulate the momentum of those old heavy generators using pure software, they aren't even considered in either of these major standards. The technology is evolving so incredibly fast that the engineering textbooks simply cannot keep up with it.
Which really brings us to the ultimate question. As we rapidly and necessarily transition to renewable energy to help save our climate, we are left with a pretty provocative challenge. How fast can we rewrite the computational laws of physics and protection standards before the grid's silent threats catch up to us? Are we literally building the green grid of tomorrow using the blind safety rules of yesterday? It's a massive hurdle, for sure, but it's one that the brightest minds in power engineering are working tirelessly to solve today. Thanks for joining me for this explainer, and keep questioning how our world works.